This video is designed to show a systematic way of balancing chemical equations. The first thing we need to do when balancing chemical equations is write out the skeleton equation. That is, all the formulas without the coefficients in front, but we need to make sure that the formulas are correct. For this system of balancing chemical equations, we'll draw tables below and above the equation. The table below will be used to count the individual atoms in the equation, and the table above will have columns showing the coefficients in front of the individual molecules. We next write the individual atoms that are in the equation, that is, we write them in the table below, and we always start with carbon for organic combustion because we'll want to balance that first, and then hydrogen, and then oxygen. We then need to count the individual atoms on each side of the equation, and in this case we have 2 carbons on the left, 6 hydrogens, and 3 oxygens. Notice that there is 1 oxygen in the ethyl alcohol, and then the 2 in the diatomic oxygen. On the right we have 1 carbon, 2 hydrogens, and 3 oxygens. Again, 2 oxygens from the carbon dioxide and 1 from the water. As I mentioned, we want to start by balancing the carbon, so we see that there's 2 on the left and only 1 on the right, so we need to add a coefficient of 2 in front of the carbon dioxide. We add that 2 in the lowest row of the table above, in the column that goes above the carbon dioxide. We then need to recount our atoms in the equation on the right. Now we have 2 carbons, 2 hydrogens still from the water, but now we have 5 oxygens, 4 from the carbon dioxide and 1 from the water. Next, we'll balance the hydrogens. We have 6 on the left and only 2 on the right, so we need to add a coefficient of 3 in front of the water molecule on the right. Now we can count the atoms on the right again, and we have still 2 carbons. Now we have 6 hydrogens, and now we have 7 oxygens. If we add a 3 to the diatomic oxygen on the left, that will give us 6 there, plus we have the 1 from the ethyl alcohol, so it will give us a total of 7 oxygens. Of course, we need to count to make sure that now everything balances. We do have 2 carbons on the left and 2 on the right, 6 hydrogens on the left and 6 on the right, and now we have 7 oxygens on the left and 7 on the right, so everything balances. To complete the process, we just bring down the coefficients from the table above, and we'll see later that if there's more than 1 coefficient in a column, we would use the one that's on the top. Here's the equation for iron 3 sulfide combustion. It still involves diatomic oxygen, since that's the definition of combustion, but now it creates iron 3 oxide and sulfur dioxide gas. The first step again is to draw a table above and below the equation. The table above will be used to show the coefficients in front of the individual molecules, and the table below will be used to count the individual atoms on each side of the equation. We first list all the atoms in the equation, again leaving oxygen for the last one, so we have iron and sulfur, and then oxygen. The count for the atoms on each side of the equation are listed in the table below. In this case, we have 2 irons on each side. We have 3 sulfurs on the left side and only 1 on the right side, 2 oxygens on the left side and 5 on the right side. Again, 3 from the iron 3 oxide and 2 from the sulfur dioxide gas. Again, we'll wait for oxygen, so we'll start with sulfur, and we see that we have 3 on the left and only 1 on the right, so we need to add a coefficient of 3 to the sulfur dioxide. The count on the right now is 2 irons, 3 sulfurs, so both of those are balanced, and we have 9 oxygen, but only 2 on the left. Since we have an odd number of oxygens on the right and a diatomic oxygen on the left, we'll use the trick where we double every molecule except the diatomic oxygen. In this case, we would put a 2 in front of the iron 3 sulfide, a 2 in front of the iron 3 oxide, and we would double the 3 on the sulfur dioxide, so that would give us a coefficient of 6. The count on the left is now 4 irons, and we have 4 irons on the right. We have 6 sulfurs on the left and 6 on the right, but we still only have 2 oxygens on the left and 18 on the right. If we add a coefficient of 9 in front of the diatomic oxygen, we should get to 18. And sure enough, we do when we count the oxygens after we add the 9. So now we have 4 irons on the left and right, 6 sulfurs on the left and right, and 18 oxygens on the left and right. We then bring down the uppermost coefficients from the table above, which gives us 2 iron 3 sulfides, 9 diatomic oxygens, 2 iron 3 oxides, and 6 sulfur dioxides. Here's the equation for iron 3 oxide reacting with carbon. It doesn't have any diatomic oxygen, but it's still a bit of a challenge to balance. We again draw our tables above and below, and we have oxygen as the last atom in the list, so we just have iron, carbon, and oxygen. The initial count is 2 irons on the left, only 1 on the right, 1 carbon on the left and 1 on the right, and 3 oxygens on the left and 2 on the right. This is where it gets a little tricky, because in order to balance the oxygens, we're going to have to get to 6 on each side. In order to do that, we're going to have to multiply the iron 3 oxide by 2 and the carbon dioxide by 3. That does, in fact, get us 6 oxygens on each side, and now we have 1 carbon on the left but 3 on the right, and 4 irons on the left and only 1 on the right. Fortunately, iron and carbon exist as just individual atoms, so it's easy enough to balance them. We can start with the iron by just adding a 4 in front of the iron on the right. That balances the iron, but we still have 3 carbons on the right and only 1 on the left. In this case, we simply add a 3 in front of the individual carbon on the left. That balances the carbon, so now we have 4 irons on the left, 4 on the right, 3 carbons on the left, 3 carbons on the right, and 6 oxygens on the left and 6 on the right, so everything balances. We just bring down the coefficients from the table above, and the equation is balanced. This approach also works with polyatomic ions. As an example, calcium phosphate reacts with sulfuric acid to produce calcium sulfate and phosphoric acid. In this case, we have 4 substances in the table below: calcium, phosphate, sulfate, and hydrogen. The initial count is 3 calciums on the left, only 1 on the right, 2 phosphates on the left and 1 on the right, 1 sulfate on the left and 1 on the right, and 2 hydrogens on the left and 3 on the right. We'll start with adding calciums to the right by adding a coefficient of 3 in front of the calcium sulfate. That brings our count to 3 calciums on the left, 3 on the right, still 2 phosphates on the left and 1 on the right, 1 sulfate on the left, and now we have 3 on the right, and we still have 2 hydrogens on the left and 3 on the right. Since we added sulfates on the right, it makes sense to add sulfates on the left, so we'll put a 3 in front of the sulfuric acid. That balances the sulfates, and the calcium is still balanced at 3 and 3. The phosphates now still have 2 on the left and 1 on the right. Sulfates have 3 on the left and 3 on the right. And the hydrogens now have 6 on the left and 3 on the right. So let's go ahead and try and balance the phosphates by just adding a 2 in front of the phosphoric acid. That in fact balances the phosphates and the hydrogens. So we have 3 calciums on each side, 2 phosphates on each side, 3 sulfates on each side, and 6 hydrogens on each side. We bring those coefficients down, and we have a balanced equation.